Okay, so I mentioned, I think in the second lecture, that there's combinational logic where you have a logic circuit that calculates an output as a function of the inputs at any given time. Then in the last lecture we said, well, there's actually a propagation delay. So whenever you change any of the inputs of a combinational logic circuit, it updates the output as soon as it can once the signals propagate their way through the gates. So there's a propagation delay. And then I mentioned in the second lecture that there's sequential logic, which is a logic circuit that has memory where the outputs are a function of not only the inputs, but the history, the recent history of inputs, the input history. And this is something that, this is one of the beefs I have with 211. They don't cover sequential logic, right? You guys remember that? They just introduce it. Sequential logic is used whenever you need to design anything that needs to be sequenced, any circuit whose behavior has to be sequenced according to the cycle, clock cycle. And that has to, like bus controllers or any kind of controller that controls the sequence of things across multiple clock cycles. So there's a few definitions here. State refers to all the information the circuit maintains in terms of its memory and the information necessary to explain its behavior, future behavior. State, for instance, could be like if I'm designing a bus controller, a lot of buses are arbitrated. Or even, I shouldn't say buses, switches. A lot of interconnects in general are arbitrated because there's a possibility that you'll have multiple ports or masters that want to go to the same output, that want to talk to the same host, the same slave. And when that happens, you have to make somebody wait. So a bus controller would, for example, have a state where you would have requested access to the bus, you request bus mastership, and then there's a state where you're waiting to receive the mastership, then there's a state where you actually do the transaction, and then there's a state where you go back to waiting for a request. You guys with me? So the state refers to the state of the controller in the sequence, where the sequence is, I have to request the bus, I have to wait for the bus, I have to do my transaction on the bus, and then I return back to idle. And sequential logic circuits include, in addition to gates, they include memory elements, which are generally flip-flops. And there's also this concept of a latch, too, which I'll cover in a minute. But basically, these are the memory elements. These are the things these are the logic elements that keep track of the state. And then a synchronous sequential circuit refers to a circuit that includes both combinational logic and these memory elements, which they refer to as a bank of flip-flops in this slide. Okay, so you guys have already designed some sequential logic circuits in Lab 1. Actually, Lab 2 you do as well. The test bench is kind of a sequential logic circuit because you've got the sequencing of vectors that it sends the ALU, but it's not synthesizable. But in Lab 1, you designed a shift register that shifted 1 bit per cycle. So in that case, the state was where the light, what the value of the LEDs, or the value that was being driven to the LEDs, so where that single LED, that lit LED was at, the location of it. But that's not it, because you also had to keep track of which way you were shifting it. So you had like 26 positions where the LED could be located at any one time, and then there was also this notion of, am I going to the left or am I going to the right? So there's like 52 states that the system could be in. Make sense? Okay, here's another example of a Verilog module that has state, This is a 6-bit counter. It has a clock input, a reset input, and then it has these 2 additional inputs for enable up and enable down. And then there's an output, a 6-bit output called count. This thing will, it's kind of like the shifter in which it'll count. Instead of shifting, it does a count. But you can count up or count down, and its state is whatever the current count is. So in this case, the state is stored in this count output. And then if you look in this always block, it provides a way to reset the count, and that should say 6'0". But I reset the count to 0 on reset. And then if on each clock edge, if reset is low, is not asserted, then if the enable up is asserted, then it will add 1 to the count. And if an enable down is asserted, it'll decrement the count, right? Make sense? And if neither one of them is asserted, then it'll just maintain whatever the current count is. And what happens if they're both asserted?
It'll just count up.
It'll count up because, yeah, that's the way the up functionality is given priority because it appears it's checked before the down, yeah, the way that that's written. So if you had them both asserted, it would count up. So this is it's sequential logic. You have state, it's a count, and then there's the combinational logic part of this would be the adder and subtractor in there. Okay, so have you guys ever heard of a latch? Did they cover that in 211? So a latch and a flip-flop are 2 sequential logic elements. They have slightly different behaviors, though. Both of them have a clock input. So, clock. You're in a CPU. The data paths are driven by the clock. They're moved forward. They're evaluated in each clock cycle. So the clock, and we'll talk about this a little later in the lecture, but the clock period, the clock speed, is determined by the maximum propagation delay of your logic in the system. But latches and flip-flops have a clock input, which is assumed to be some regular periodic square wave. A latch will take whatever's coming in the input, which is called D, and the input is, by convention, is called D in both a latch and a flip-flop. I think D stands for data. I don't know what Q stands for, though. Never figured that out. But D is the input, Q is the output. These are also driven with they're shown with a complemented form of Q. So in a latch, the clock acts kind of like a gate where when the clock is asserted, then, when the clock is asserted, so whenever the clock is high, it will take whatever D is and it'll let that flow through directly to Q after some propagation delay. That's why you notice that there's a little bit of a gap in time between when D rises, and it rises while clock is high, notice. So D rises and then Q rises in response to that. Okay? But when, and that happens again here, D falls and Q falls because that happened when the clock was asserted. But over here, D falls and then rises, has a falling edge and a rising edge. But because that happened when clock was not asserted, the Q output didn't change. So that's the memory portion of this. Whenever the clock is low, then the latch will maintain whatever the previous, whatever its previous state was, which was whatever the value of D was the last time, or the last time the clock was asserted. You guys with me? Make sense? Okay. So these are level sensitive. level sensitive, the latch. The flip-flop, on the other hand, uses the edge of clock. So I like to think of it like, you can think of a flip-flop like a camera, where whenever you have a rising edge, or it could be falling edge, depending on how you design the flip-flop, but in this case it's a rising edge active flip-flop. Whenever the clock goes from low to high, whenever there's a rising edge or positive edge, then the value of D at that moment in time is captured and then stored inside the flip-flop and kept there until the next rising edge. Okay. In Verilog, we design our sequential logic with this behavior, with this flip-flop behavior, not with the latch behavior. You want to try to avoid using latches in your designs. It's much easier to design circuits with this flip-flop type behavior. If you're not careful, though, you can accidentally write system Verilog that infers the behavior of a latch. And if you do that, you'll actually get a warning message when you go to compile your design in Quartus. I don't know if ModelSim warns you for that, but I know Quartus does, although you might miss it because it outputs a lot of stuff. Any questions about this? Okay, so I covered this before, so I'll go through this quickly. But you can make a flip-flop easily. You just use this always_ff construct in Verilog, and then you have the sensitivity list, which is pos edge clock, or you can say neg edge clock if you want the falling edge. And then inside there, the convention is to use a non-blocking assignment, which is the less than equal sign, and then you can make assignments in there. And you don't have to. It doesn't have to just be one assignment. You can set several things inside one always block. But the point is that always block only activates on the rising edge of the clock. So it's only, the outputs are only updated on the rising edge of the clock. So this is something that you're going to use a lot in your CPU design, because we're designing a pipeline CPU, and so all of your pipeline registers will be set up this way, where they'll all be set they'll all be set after the rising edge of the clock. And anytime you need to delay a value from one cycle to the next, like for example, if you need to carry a signal forward one cycle. So for example, we're going to be implementing branch instructions, and if you remember from 2.12, branch instructions have this notion of a control hazard. That's when you're executing the branch, or you're resolving the branch, because if you're in a pipeline CPU, you'll already be fetching the next instruction after the branch while you're determining if the branch is going to be taken or not, right? That's just the nature of pipeline CPUs. In other words, by the time you realize whether or not you're going to take a branch, you've already fetched the next instruction. So in our CPU, we're going to have this, we're going to calculate if you take the branch, we want to zero out, we want to stall, meaning we want to squash the next instruction that's already been fetched. But we don't want to do that until the next cycle. So we'll have a stall signal that'll be set up in one of these always flip-flop blocks that will be asserted in the next cycle. You guys with me? It's a way to delay a cycle. It's a way to carry a signal forward from one cycle to a future cycle. You use these this type of behavior. Now, this is something that's always confusing. Registers can be, it's kind of a vague term, because if you have multiple flip-flops that are implemented together to create like a multi-bit flip-flop, that's referred to as a register. But you guys know from 2.12 that when you write an assembly language, there's also a notion of a register in instruction set architecture and assembly language programming, right? There are two different registers. A register in an assembly code is an addressable memory value, where you actually send an address into a register file. It acts like a RAM, right? Whereas a register in Verilog is something that is not addressable necessarily. It's just like a multi-bit flip-flop. Does it make sense? It's a little confusing to have both of these things named the same thing.
So
Question?
basically, anywhere where we would see a multi-bit flip-flop, the term is just register.
Register, yeah. We don't call them flip-flops. I don't know why. It's the
So
same.
just contextually, then, like, we'll know when we're dealing with the MIP stuff. Register in context of the register file. We'll just have to look and see.
Right. Yeah. This is an example of it.
Yeah.
So this is a 4-bit register, but it's not the same as a MIPS register that has an address.
So like a MIPS register is like part of the instruction set, and this is just any bytes.
Yeah, the difference is whether you're at what level you're at. Like if you're in the microarchitectural level, then that's a register. If you're in the instruction set architecture level, then a register is a numbered
Okay.
location in the register file. Okay, I covered this too last time, but just to briefly review, you can now also have a flip-flop or a register that is enabled, meaning that the clock will be ignored. It'll ignore the clock, the rising edge of the clock, if the enable is not asserted. And we already kind of saw that with this counter too. So in this counter, if both of these enables, enable up and enable down, were both not asserted, then nothing happened on the clock edge. It would ignore it. So if you have an enable signal in a register flip-flop, it's usually shown as part of the symbol. The book has this thing where it shows, it's showing, they say internal circuit, as if the only flip-flop available to us didn't have an enable built in. So in order to get the functionality of the enable, they put a mux here where the mux is controlled by the enable, and if the enable is 0, then it just feeds back the Q output back to the D. And if the enable is 1, then it'll pass the D input through the multiplexer into the D on the flip-flop. In reality, I think on the FPGA, if I'm not mistaken, registers have the enable is actually, I think, built into the circuit for the flip-flop, or for the flip-flop. So you don't necessarily have to worry about building one up like that. Okay, and then of course there's another option for flip-flops. There's a reset, where if you assert the reset, then it'll clear the value of the flip-flop or the register to 0. Alternatively, you can even have a set too that'll set it to 1. So why would we ever need that? Anyone know? So when you have flip-flops and you power them on, they come up in a random configuration, random state. So in this, even on an FPGA, they'll come up, well, it's a little bit more complicated. With an FPGA, when you program the FPGA, it'll clear all the registers automatically for you. But in an ASIC that's not programmed, that's actually an actual custom chip, the registers, all the RAMs on there and all the flip-flop / registers will come up random. So the reset is used to initialize the flip-flops to a predefined initial state. Back when I was in school, we called it the sanity state, meaning that it was a known starting value, and the reset had to actually be pulsed. So you'd fire up your chip, and the first thing you do is you would pulse a reset signal, which would be connected to every register / flip-flop in the chip. Now, how are we implementing that in this class? We're actually going to connect one of the buttons on the FPGA board to the reset. So that way, when your system is, you program your FPGA, your processor will go on there, and you can hit that button to reset it. So and you can also reset it, whenever, if it gets hung or something, you can hit that button. You guys with me? All right, so that's what the reset does. So it's you want to have a reset on your flip-flops. Resets can also be synchronous or asynchronous. Synchronous resets them only on the clock edge. So a synchronously reset flip-flop will reset, but you have to have the reset input enabled, asserted, and you have to have a clock edge. So meaning that there's a delay. Like you tell it to reset, but it doesn't reset right away. It resets on the next rising clock edge. An asynchronous reset will reset it immediately. The FPGAs support asynchronous resets natively. So there's no reason, I've never seen a compelling reason not to use an asynchronous reset. In Verilog, it's a little bit more typing though, because if you have a synchronous reset, you don't have to put the reset in the sensitivity list. Only the clock is in the sensitivity list. But to get an asynchronous reset behavior, you have to make sure that the always block triggers whenever the reset changes, or not just changes, but goes from 0 to 1, so pause edge reset. So you'd have to list that in the sensitivity list. Any questions? Okay. And I mentioned you can also set. This is not very common though. Set is just like reset, except it allows you to initialize the output, the Q value to 1. Okay, so how do you design synchronous circuits? Well, there's sort of there's sort of a formal and an informal way to do it. We already designed, as I mentioned earlier, we've already designed synchronous circuits in this class by putting in shifters and counters and that kind of stuff. Another way to do it is to build a synchronous circuit as a finite state machine, as a design that explicitly shows states and transitions between states. The book has some rules for synchronous logic design. I mentioned the registers contain the state of the system. State changes at the clock edge, so the system is synchronized with the clock. And then they have the rules are every circuit element is either a register or a combinational circuit. So what else is there? Don't put latches in. I think that's the idea. At least one circuit element has to be a register. If not, then it's just combinational. All registers receive the same clock signal. Now think about that. That's kind of crazy because how many registers do you have on a chip? There's a lot. So that clock comes in and it gets fanned out to a whole lot of registers on the chip. So ASICs and FPGAs have specialized wires for the clock that are designed as a kind of like with a special structure, right? And then every cyclic path contains at least one register. So you don't want to have cycles in your logic circuit unless the cycle is broken by a register. So this is this kind of I can explain this with the example I used earlier with the stall signal. So in your CPU, if your CPU fetches a branch, and when that branch instruction gets to the stage of the pipeline where it's resolved, determined if you should be taking the branch or not, you want to set a stall signal that will take effect in the next cycle when the next instruction that appeared in the program after the branch reaches the stage where it otherwise would be evaluated, but we want to step on it, right? We want to replace the instruction that appeared after the branch with a bubble, right? A no-op, right? We want to cancel it out. Does it make sense? You guys with me on that? I'm assuming you remember some of this stuff from 212. Okay, so one of the common mistakes that students in this class make is they'll forget to put a delay for that stall signal. So what will happen is is the stall will not affect the next instruction, it'll be affecting the current instruction. So what you'll end up with is a combinatorial loop where the control unit will say, oh, I got a branch, and oh, the branch should be taken, so I'm gonna have to stall. So it initiates the stall, but the stall cancels the branch. So then the control unit will say, oh, I have a stall. I mean, I have a no-op, so I don't have a branch, so I'll deassert the stall. So it deasserts the stall, and as soon as it does that, the branch reappears. And then it says, oh, I have a branch. And it goes into this loop, that's this endless loop. And in the simulator, if you do that and you simulate in ModelSim will hang. It'll just freeze. And then you're in trouble because there's no recourse at that point. There's no good way to debug that aside from like commenting out half your code and seeing if that resolves it. And if it does, you know that wherever the problem is, it was in the half that you commented out, right? So that's a problem that you might encounter in this class. So you have to be careful that if you have that kind of a cycle where you have a signal that could affect the evaluation of that signal, there needs to be a flip-flop in there that interrupts that cycle. So that's what they're talking about there. Okay, and then two common types of circuits are finite state machines, as I mentioned, and pipelines. Okay, and I mentioned this latch. Let me revisit this latch issue again too. If you have to be careful when you have an always block, you have to make sure that if you're trying to design combinational logic with an always, you set all the output signals every time that always statement is activated. So this is a problem if you have an if statement. Obviously, if you have an if statement inside your always, you may accidentally infer a latch if you don't assign all the possible outputs from every path of the if statement. Now, this problem has kind of gone away because in System Verilog, we have this difference between always FF and always comb. And if you put an always comb, you're telling System Verilog that you're intending to make combinational logic. So if you make that mistake, you'll get an error message. You'll know you made the mistake. And this is the reason they did this. This is the reason why we have different always statements. In regular Verilog, which is what we taught in the past in this class, that was a big concern, but I think this hopefully will fix the problem, I hope. Although, I actually tested this, you can still make a latch with an always FF and you will not get an error, which is kind of disappointing. I was hoping that the always FF would force you to make a flip-flop. You guys with me? Or to have, when I say flip-flop, I mean edge triggered as opposed to level triggered. There's always an always underscore latch as well, and I don't really know the difference between them. Make sense? So anyway, the point is that I think we should be okay as long as you use the always FF to make your flip-flops and your always underscore com to make combinational logic. Okay, so let's talk about finite state machines. I mentioned, so sequential logic is what you use for finite state machines and pipelines. We will be creating a pipelined CPU in this class, but we're also going to be designing a finite state machine in the next lab because there's a step before we get to the CPU. We're going to create a calculator on the FPGA, a reverse Polish notation calculator, and for that we're going to use a finite state machine. You guys know what a RPN? Have you ever heard that? Reverse Polish notation. So that's the calculator with a stack in it. And so a stack, we're going to create a hardware stack, right? A hardware, not a, because you guys you can make a stack in software, or you can make one in hardware. So we're going to make a hardware stack, and we need a finite state machine to control it because we're going to have to sequence operations to that stack. Because in an RPN calculator, the idea is that you push values onto the stack, and then you do an operation. And when you execute an operation, you have to pop two values off the stack, generally, do the operation on those values, and then you push the result back on the stack. So that, assuming that you can only do one stack operation per cycle, or one ALU operation per cycle, how many cycles is it going to take? It's going to take a cycle to pop, another cycle to pop, a cycle to calculate, and a cycle to push. So it's going to take 4 cycles. So we're going to have this sequencing that has to happen, where once the user initiates something, it goes through a sequence of operations, clock level operations. You guys with me? So that's something we can use a finite state machine for. A pipeline, on the other hand, is when you have registers and you move data through a sequence of registers, almost like a shift register. Okay, so here's another example of something you might use an FSM for. This is the example from the book. This is a traffic light controller. So in this case, you've got 2 streets. You've got Academic Avenue and Bravado Boulevard, which are abbreviated just A and B. And there's this intersection, and you have this traffic light controller that will wait for all the traffic to flow through the intersection before it'll change the state of the lights. And when it changes the state of the lights, it goes through the yellow period as well, where it goes from green, yellow, and then red, right? So you've got 2 inputs. You've got the traffic sensor A and B, which are true whenever there's traffic on that road. So TA means there's traffic on Academic Avenue. B means there's traffic on Bravado Boulevard. And the traffic is obviously traffic at the intersection, or traffic near the intersection. And then you've got lights. Output is the lights, light A, light B. And since there are 3 possible light colors, each one of those outputs would have to be 2 bits. So you've got 2 1-bit inputs and 2 2-bit outputs. So this just shows that again. So there's a clock input, there's a reset input that resets it to a known state, and then you've got 2 1-bit inputs for the traffics and 2 2-bit outputs. There should be a 2 there, but there's notice there's like a little 45-degree line that signifies that each of those is multiple bits. So an FSM is designed with states, which are shown as circles, bubbles, circles, and arcs that represent transitions between states. So whenever there's a positive edge of the clock, so we're always in a particular state. At any clock cycle, you're in one state. And then when there's a clock event, clock edge, you can potentially change states, but you're limited to whichever states are reachable from your current state, which are shown with these arcs. And there's a little reset arrow there shows what the reset state is, the sanity state. So in this case, we have 4 states that represent the 4 states of the light. So we can have a green light on one of the 2 streets, or we can have a yellow light at one of the 2 streets, in which case the other one's red. Just like, there's a green light at one of the 2 streets, and in which case the other one's red, or there could be a yellow light at one of the 2 streets and the other one's red. So there's 4 possibilities. So we're going to assume that when we reset, we're going to have a green light at Academic Avenue and a red light at Bravado Boulevard. And you have a transition that loops back. So whenever we have traffic, as long as we have traffic on Academic Avenue, we're going to stay in that S0 state. Meaning that as long as cars are flowing through Academic, you're just going to keep that one red. At some point, when the traffic, there's no more traffic, and we have TA is false, then we'll switch states over to state S1, where we'll have a yellow light at Academic Avenue with the red light at Bravado. And then there's an unconditional transition from S1 to S2 where we have Bravado Boulevard as green. So there's an assumption here that the clock cycle length, the clock period, is set to however long the yellow light would be on for. Does it make sense? Because there's an unconditional transition here. We're going to immediately, so as soon as traffic stops flowing on Academic Avenue, we're gonna light up yellow on there, and then one cycle later we're gonna go red. Make sense? Okay, and then same thing here is we're gonna stay in this state. We're gonna have Bravado Boulevard will be green light for as long as we have traffic on Bravado. And then when the traffic stops, we'll transition it to yellow and then go back to here. Actually, in addition to the clock cycle being as long as the yellow light, there's also, if there's no traffic, what's going to happen? If there's no traffic on either straight, then it'll just keep cycling. Yeah, so it'll just go. It'll go S0, 1, 2, 3, 0, 1, 2, 3. It'll just keep cycling for as long as there's no traffic on either street, right? So the clock period would have to be, pretty long, right?
So you would just get a pinwheel of lights around
Right.
the intersection.
Right.
So like, if one had a bunch of traffic, you would never go.
Yeah, if you have a continuous stream of traffic, then it would starve out the other street. Yeah.
This light would be rough.
Yeah. Now you could add additional inputs though. Like you could have a timer and add that as another input. This was meant to be simple. So the only inputs are the traffic indicators. But you could also put timers. I think that would allow you to time out. Okay. So so you can build this next state table where. So let me back up here a minute. So the arcs. So notice there's two things. Sorry, one more step back. So we have the outputs. The outputs are labeled inside the states. That's intentional, meaning that every state has a fixed set of output values. And then the transitions are labeled with the input values, right? So the states contain the outputs. The transition are marked with the input values. So the transitions are describable with a next state table or state transition table, which is really just a truth table. But notice that on this truth table we've got the inputs, and then we've got the current state as a column and the next state as a column. So the size of this table, you have to be able to have a row for every possible input for every possible state, right? Now, and that would be a well, I guess in this case, let's see, you've got there's four states, sorry, and there's 2 bits of input, right? So that would just be 8 rows. But they've abbreviated that by putting some don't cares in. So if you're in state S0 and we have traffic on academic, then I'm sorry, we have no traffic on academic. I don't really care what the traffic on Bravado is, because we know we're going to transition to S1. And if you go back to the state diagram, you can see that the traffic on Bravado is implied to be a don't care because it doesn't show up here on this transition. Now you could label that, TB equals X or something on there, but it's not shown, which implies that it's a don't care. And actually, you could, maybe they should have put that in there, because you could have, to stop that pinwheel type effect, right? You could stay in this state, even if there's no traffic on academic, you could wait until there is traffic on Bravado before you jump to S1, right? In which case you could just say TA equals 0 and TB equals 1, right? So you can add an additional condition here to not go to S1 unless you have some traffic on the other street. But they didn't show that, so that's the TB is a don't care. And so if you're in S0 and you got traffic on academic, then your next state's going to be S1. Sorry, S0, sorry. If you have traffic on academic, you're going to stay in S0. So this is your loop back transition, this row. So you calculate, this is your next state logic. The output of this is going to go into the D input on your state flip-flops. And so even though you're calculating the next state, you're not actually moving to the next state until you get a clock edge, right? If you're in S1, then both of the inputs are don't care because you have an unconditional transition from S1 to S2. See, there's no condition on this arc, and so that's why both of these inputs are don't care, which makes it so that row only has there's only one row for state S1. Any questions? Okay. Okay, then once you have that set up, at some point you have to decide what your encodings are for the 4 states, because you have to create a state values that'll be stored in the flip-flops for each one of these states. Now this is kind of arbitrary. You can assign these any way you want, but once you've assigned them, then you capture these encodings in the next state logic by replacing the current state and the next state symbols with these binary values. And once you've got that, then you can actually convert this table into Boolean logic. So for instance, S1, if we look at the outputs here where S1 is 1, it turns out that the bit 0, sorry, hold on, let me back up a minute. So this is a little confusing, let me point this out. The states are S0, S1, S2, and S3, and notice how they, the state value has S subscript 1, S subscript 2. So this S1 doesn't mean state S1. This S1 means the most significant bit of the binary value corresponding to the state, right? The state encoding, right? So don't let that confuse you. So S1 and S2 are the 2 bits of the state. And so if my S1 and S0, sorry, if my S1 and S0 are 0, 0, that means that I'm coming from state S0, and so then I have to fill in the next state. So if I'm in S0 and I get a 0 don't care for TATB, then I'm going to transition to state S1, which happens to have the encoding 0, 1, right? And if I have traffic at academic and I don't care what's at Bravado, then I'm going to stay in S0. So the next state will be 0, 0. Everyone see that? It's just a little confusing because of the way they name the states. Okay, so then you can take this truth table and you can use, you can calculate the full sum of products Boolean for this, or you can use a Carnot map to simplify the logic. In this case, they say the next state for bit 1 of the next state, so S sub 1 prime, meaning the next value of the most significant bit of the state, which is S prime sub, or S sub 1 prime, is S1 XOR S0. Is that true? Yeah, looks like it, because if you look at this table, if you have a 0, 1, or 1, 0, or 1, 0, and S0 and S1, then you're going to set the next state bit 1 to 1. And 0 otherwise. See, 0, 0, 0, 0, and 1, 1 will give you a 0. What does this mean? It means that you can calculate the most significant bit of the next state irrespective of the inputs. Just happens to work out that way. But for S sub 0, S prime sub 0, then you do the logic here, and in this case, this is just these are the min terms for these two rows here. So this first min term is not S1, not S0, not TA, which is these three guys are all 0, and then this row has a 1 as well, and that's S1 and not S0 and not TB, right? So that's just in that case they didn't. I guess there's no opportunities there to minimize that. Any questions? So it's pretty straightforward. It's a little confusing though, because you've got like two different versions of the state. You've got the current state and the next state. The next state is shown with these, the little tick marks, the prime, whatever you want to call them, and the current state is just S0 and S1. So don't let that confuse you, right? So you've got the current state and the next state, and the current state gets set to the next state whenever the clock edge arrives, whenever you get the rising edge of the clock, so on the next cycle. Okay, and then you also have to have an encoding for the light colors too, because I think that was just shown symbolically here, right? So LA was green, LB was red, so you have to come up with encodings for the outputs as well. And so in this case, we have the output logic is just a function of whatever state we're in, which makes sense because the outputs are associated with the states. So we don't care what the input is for the output logic in this case. Make sense? So what does this mean? This means that you need two combinational logic circuits. You need one that sets the next state logic, the next state function. It takes whatever the current state is along with the inputs and calculates the next state. Then you need a separate circuit that takes the current state and translates that into a set of sorry, that's the wrong slide. Translates the current state into a set of outputs, right? So that's what this table does. So you've got the four states with their encodings, and then you've got in this case there's four outputs. There's two 2-bit outputs, and then we've got four Boolean logic expressions that will generate each of the four outputs as a function of the current state. So notice there's no tick marks, there's no primes in here. This is the outputs are only a function of the current state. Everyone with me? Okay. Okay. So as I mentioned, you've got the state is held in a register. Or you can think of it as a bunch of flip-flops where you have one flip-flop per state bit. So in that example, there's 2 state bits, so we'd have 2 registers that hold the current state. The flip-flop's output is giving you the current state, and the input is the next state. So both, in this case, they show this S prime and S. They're both connected to the register, but one is the input and the other one's the output. So that way, whenever you get a clock edge, it will capture whatever's coming in as the current state. It'll capture whatever's coming in will get captured in and become the current state. And then you have a block of logic, combinational logic, that calculates the next state value, it's the next state logic, and you've got another block of logic that calculates the output logic, or that takes the current state and transforms that into the whatever output values correspond to that state. Okay, so I mentioned that in that example, the outputs are only a function of whatever state you're in, but that's actually a style of finite state machine called a Moore machine. You can also, there's a slight variation on that called a Mealy machine, where you can also bring in the inputs and make the inputs determine, along with the current state, what the output value is. Now that has a consequence, is that the output will no longer necessarily only change on the clock cycle. That will make the output asynchronous, right? Because that way, if the inputs are allowed to affect the output, then even within one clock cycle, the inputs could be toggling, and that may potentially be changing the output even within a clock cycle. Whereas if you design it as a Moore machine, the outputs will only change on once per cycle, right? You guys with me? Another consequence of the Mealy machine is, I don't know if the Mealy machine will also require that the outputs, you have to move those from the states to the transitions, because the transitions are where you're looking at the input values, right? So you can always tell just looking at the state diagram whether it's a Mealy machine or a Moore machine. In a Moore machine, the outputs will be inside the state. In the Mealy machine, you actually list the outputs on the transitions. In most cases, it's, at least in my experience, it's common to just design state machines as Moore style, right? The way I always thought of it, the way I remember the terminology was more is less, in the sense that a Moore machine has less complexity than a Mealy machine, which is a little bit more complex because you have to consider the output logic is more complex because it involves both the state and the inputs, as opposed to just the inputs. Okay. Okay, so designing these in logic, so this is a representation of the state logic where you have this, kind of long flip-flop that has 2 inputs and 2 outputs. So this is a register, 2 bits, 2-bit flip-flop or register, and the next state logic, which we had in Boolean form here. So the next bit 1 of the state, so S sub 1 prime, the next most significant bit of the state is the previous current state values XORed. So if you look at the logic design for that, you see that you've got S1 and S0 come out of the state, the flip-flop, the register, and they feed back around and they go into an XOR gate, which the output of which goes into the next S1 value. And then remember that the next state value for bit 0 was the 2 min terms, so it was a sum of products. Sorry, so the two AND gates and the OR gate. Make sense? So that's the next state logic, and then the output logic is, in this case, is shown on the right-hand side, and so this will give you the 4 output values, which is 2 bits per light value, and these gates were set up according to this Boolean logic, which came from the truth table. So it turns out that the most significant bit of the light output for Academic Avenue is just bit S1. So that should feed straight through, right? Yep, there it is. It branches off of there and just goes straight out, right? Whereas bit 0 of the academic avenue light signal is not S1, S0. So there's not S1 is shown here with a bubble on this AND gate, and S0 is the second input on this AND gate. So there's, bit 0, and then the other ones are set up the same way. So that's the whole traffic light controller. Okay, so when you're debugging this, you're simulating this, you're gonna see it on a waveform. This is similar to what ModelShem would show you when it's running. So we've got the clock at the top, and so as you go from rising edge to rising edge on the clock, those are the individual cycles. So cycle 1 is the first rising edge of the second rising edge, cycle 2 is the second rising edge of the third rising edge, and so on. So we have all these cycles, and you'll notice that the light values are all asserted for a integral number of cycles because it's a Moore machine. So notice that this is academic light here. It's green for how many cycles? 1, 2, 3 cycles. Yellow for 1 cycle, red for 3 cycles, green for 2 cycles, right? So if we follow this through, and we have a reset too, by the way. So when we start out, I mentioned that these flip-flops will come up as it will come up as a random configuration when you power them up. So that's why they're showing question marks here at the beginning. The reset signal will cause them to cause the state to go to 0, 0, 0, 0. Sorry, just 0, 0. State is 2 bits, 0, 0. And then because the state is 0, 0, that will cause the academic light to go green and the bravado light to go red. And then nothing will happen here while the reset is high. So as long as you hold reset high, the thing is the controller is going to be crippled. So we can't really even start evaluating what happens here until after reset drops. And even then, we don't really care about anything until the next rising edge. We know nothing's going to happen until the next rising edge after the reset drops. So the reset drops here during cycle 2, and then we have a rising edge here that's the start of cycle 3. And at this point, we know that we have a green light at academic, and the question is, are we going to change states? Is there any traffic at academic? Well, yeah, there is. So at that point in time, on that rising edge, the traffic for academic is high, so we're not going to switch states. In fact, it stays high until cycle 4, right? But the problem is, notice, now this is a subtlety, but notice that the traffic at academic drops, but it doesn't drop until after cycle 4 begins, which means we're not going to actually switch states until cycle 5, the following cycle, right? Because it's going to take, we're not going to see that, even though it dropped right there, right by that clock edge. Look at that, it fell. That traffic fell right at that rising edge, but it doesn't matter, it's too late. The traffic at academic didn't die down until after that rising edge, so we're not going to catch it here until the next cycle, at which point we will go yellow on academic, right? Now you'll notice, well, wait a second, hold on. Look at that. That drop in this traffic immediately caused S prime to become S1. Well, yes, because the next state logic is combinational, right? So the next state logic will update immediately in response to the inputs, but that won't take effect and become the current state until the following cycle, which is why you have a delay here between when you switch to S1 here and when you switch to S1 here. You guys with me? Okay, so once we go into, let's see, yellow light is here. We're only in one, yellow light is only asserted for 1 cycle, and then the next cycle we're in red. And then once we go red on academic, then that also triggers a transition to green on bravado. And we're going to stay in that cycle, it's that state, until there's no traffic on bravado, which doesn't happen until, again, it happens in the next cycle, but it happened too late for us to begin the transition in cycle 7, so we wait till cycle 8, and that's when we go into yellow on Bravado. You guys with me? Now, another thing about this timing diagram that's a little confusing is that in Model Sim, when you look at this, a lot of these things will be happening at the same time because there's no, I mentioned last lecture, there's no propagation delay in Model Sim. So if you notice that, like when there's a rising clock edge here and there's a transition that happens in response to that clock edge, notice how they put a little, notice how that clock edge rises right in the middle of that dotted line there, right? But the change in state, you see they put a little bit of a delay there? So they don't change state right on the dotted line. The dotted line signifies the rising edge, but yet the state doesn't change right on the dotted line, right? Because they're trying to show that there's a little bit of a delay. It takes a little bit of a propagation delay before the state will change, right? Because the flip-flops are not instantaneous. They don't change immediately on the clock edge in reality. But in Model Sim will show that. Model Sim will have these things changing instantly, right? Because Model Sim doesn't have any notion of propagation delay. Okay, so it's a little, that part is at least I found that confusing. Okay, let's skip over that. Let's jump to this. So this is an exam question I asked in the last year in this class for this chapter. This was a not from the book. I came up with this one myself. So I said, you are designing a controller for an elevator in a 2-story building. The controller has the following inputs provided by the buttons outside the elevator on each floor. These inputs assert when a user pushes a button and deassert automatically when the elevator is idle at the corresponding floor. So it's, you hit the button, it calls the elevator, and it stays asserted until the elevator gets there. So the elevator controller sees all of the inputs on all of the floors. Now, in order to simplify this, I just have 2 floors. So there's a first floor button that says I want to go up, and there's a second floor button that says I want to go down. And since there's only 2 floors, there's only 1 on each floor. The controller has the following inputs connected to the buttons inside the elevator, which assert when a user pushes a button and deasserts when the elevator reaches the corresponding floor. So if you're in the elevator, there's a button that says floor 1 and floor 2. The controller has the following outputs: go up, go down. The elevator must maintain state that track its current floor in its current direction, or lack of direction if it's not moving. The elevator requires 1 cycle to move 1 floor and must stop moving to allow passengers to board. Sketch the finite state machine as a Moore machine. You don't need to design the logic. Be sure to specify the reset state. So how would you design that? How many states would it have, first of all? The elevator has obviously would have to have a state that indicates what floor it's on, right? So it has to be, its state would have to be, I'm on the first floor, I'm on the second floor, right? But also, because there's a sequencing that has to happen where it has to assert an output for 1 cycle to go up or down, to activate the motor to go up or down, it would also have to not only know what floor it's on, but what it happens to be, if it's idle or if it's moving, right, as well. If it's on the first floor, it can be idle or it can be moving up, like trying to go up, right? And if it's on the second floor, it could be idle or it could be going down. So there's 4 states, should be 4 states on this thing, right? So first floor idle, first floor going up, second floor, idle. Second floor, going down. Okay, so if you're on the now the first floor idle, we'll make that our reset state. So we'll assume that when you power the system up, the elevator is on the first floor. Otherwise, it'll be confused. So that's how we'll initialize the system. If somebody pushes, if it's on the first floor and it's idle, and somebody pushes if someone on the second floor pushes the button to call the elevator, then it has to go up to get that person, right? So we'll have a transition here that's F2. Floor 2 is calling the elevator, so it's got to go up. While it's going up, it can't do anything for that cycle because it's moving, but then once it reaches the second floor, we'll assume that as it reaches it, it'll go idle on the second floor. So there'll be an unconditional transition between the going up state and the second floor idle state.
If there's an unconditional transition, is that truly a state then?
Yeah, because the idea is that we want to spend a cycle in this state. The reason we have this state with the unconditional transition is because it says in here that it requires one cycle to move one floor, right? Okay. So we want to pass through this state to give it that travel time, okay, right? But then it's unconditional because it only takes one. Now, if it took like 10 cycles, then we'd have 10 states. It would go through 10 states. Okay. But it takes one state to move. And then we get to the second floor, idle. And if we're on the second floor idle, we can go down, likewise, if we get an F1 request from the first floor, unconditional transition here. And then if you're in the elevator, there's go up and go down. So if you're in the second and you go down, then this would be, will go down. So this would be F1 or go down, right? Likewise, if you're on the first floor and you're someone in there, then they push the go up, yeah. Sorry. Then it'll go up. All right, and that's it. Oh, sorry, and there's I forgot the outputs. Sorry, that's the output. Sorry, sorry, I screwed that up. The outputs are go up, go down, right? So so this would be going down would be go down equals 1, and this would be go up equals 1, right? And then if I don't mark it, the assumption is 0, right? But I'll put them in just to be clear. So go up equals 0, go down equals 0, go up equals 0, go down equals 0, and then if you're going up, then you can't go down at the same time. Go down, go up, 0.
This may be a little tedious in the state machining, but like if you're on the first floor and you hit the F1, then they'll loop back into itself.
Yeah. Well, that's implied. Yeah, when you design the next state table, when you have to fully enumerate every combination of things, then yeah, you would actually have to stay in that state in that case. So the loopbacks are usually implied. If you don't draw an arc, like if you don't satisfy any of the conditions of an outgoing transition, then the assumption is you're going to stay in that state. Yes?
Should we expect this on exam 1?
Yes.
Okay.
Yeah, this is the kind of question. I'll ask something just like this. Yes?
What about that reset state mentioned at the end?
Oh, that's it. I drew a little.
Oh, okay.
That's what that little arrow there was.
So it'll always, do we have to account for the elevator randomly resetting during operation?
No.
We're assuming at time of installation, we're going to be in this.
Yeah. The idea is that whenever you reset it, it would have to physically be on the first floor.
Okay.
Because if it was on the second floor and you reset it, the controller would think it's on the first floor, even though it's physically on the second floor. So that would be problematic.
Okay, that was like a case of like the real world, I have questions as a result of it being in the real world. Okay.
And what about first floor request up? That was right. So that was the one I forgot. I was confused earlier. So far we've accounted for the first and the second floor call buttons, and we've got the outputs. The one thing we haven't put in yet are these two. So if you're in the elevator, it's F1RU. How's the following inputs connected? Sorry. I'm sorry. I screwed that up too. This is F2RD here. Yeah, and this is F1RD. Yeah, because those are the ones outside. Those are the outside the elevator, and the ones inside the elevator are floor 1 and floor 2. But those ones would actually work the same way, because if you're on the first floor and you push the floor 2, so this would be OR floor 2, and this would be OR floor 1. There we go. Now we got it. Everyone with me? So if you're the floor 2 request down is if that's the call button on the outside of the elevator, right? As opposed to the F2, which is the button inside the elevator. But either way, either one of those will cause it to go up if it's on the first floor. Everyone see that? Okay, so let's look at an example of another example that'll include a Mealy machine. This one's from the book. Alyssa P. Hacker has a snail that crawls down a paper tape with 1s and 0s on it. The snail smiles whenever the last 2 digit has crawled over a 0, 1. Design more Mealy FSMs of the snail's brain. So this is a pattern matching problem. You're looking for a pattern of 0 and 1 that come in sequentially, right? So in a Moore machine, don't forget about this for a second. In a Moore machine, we'll have a reset state at S0. If the snail sees a 0, it'll travel to this S1 state that serves as an intermediate state. That means I've seen part of the pattern. I'm looking for a pattern 0, 1. I've seen half of the pattern, right? At which point I can see the second half. If I get a 1, I'll go to state S2, where I'll say smile, the smile output. Or if I see another 0, I'll stay in that state, because as long as I keep getting zeros one after another, then I'm always in this sort of, I've seen half the pattern, right? But if I see the whole pattern, if I see 0, 1, then if I see a 0 right after that, I'll go back to the intermediate state. Or if I see a 1, I got to go back to the start state. I got to completely reset, right? You guys with me? So probably the easiest way to show that would be if I show a sequence of if I have a sequence of values, so 0, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1. So I start out, I see 0, I'll be in state 0 at the beginning. I see 0, I'll stay in S0. No, sorry, I won't. Actually, sorry, I'll go to S1, because 0 is the first character, right? So I'll go to S1. I see another 0, I'm going to stay in S1. If I see a 1, sorry, how many zeros? I got 3 zeros, so I'll stay in there for 3 states. Then if I see a 1, I'll go to S2. If I get another 1, I got to go back to S0. Then if I see another 1 again, I'll stay in S0. Then I'll go to S1, and then S2 because of 0, 1. And then S1 and S2. So this 0, 1 will get me the smile, right, the S2. And then I've got another 0, 1 here. That'll get me to S2. 0, 1 here gets me to, oh, sorry, it should be S1, S1, S2, right. Guys with me? Yes?
Why do we need that intermediate state of S1 when it's
So-
only 2 states either on not smiling or smiling?
Because we're seeing one bit every cycle. So when we've seen half there's 0 is a prefix. It means it's the first part of the pattern I'm looking for. So that state S1 is it's like I've seen the 0, I'm expecting a 1. If I don't see the 1, then I'll stay in S1 because that means I've seen another 0. There's only 2 possibilities. So if I see 2 zeros, then I'll stay in that state because I'm still in this perpetual state of seeing only the first part of the pattern, not the second part. When I eventually do get a 1, I'll go to S0. At which point, if I get a 0 right after that, I'll go back to S1. I'll short circuit it back to S1. But if I get a 1, then I have to go all the way back to S0 because it'll take at least 2 more cycles after that point before I'll see the complete pattern again. So that's the Moore state machine. Now you could design a simpler version if you design it as a Mealy state machine. I mentioned earlier that in that case, you're going to take the outputs and you're going to associate the outputs with the transitions instead of the states. So you end up having to put every state has multiple. You could assert different outputs in the same state depending on what your input is. So in this case, if I'm in S0 and I get a 0, I'll go to S1. But while I'm in S1, if I get a 1, I will assert 1 and go back to S0. So that way the S0 state is used as the reset state. The S1 is both the output 1 state and the intermediate state because I can output a 0 or a 1 while I'm in S1. Right? So in this case, I've got, if I'm in S1 and I get a 0, I want to stay in that state and output 0. And if I get a 1, then I can output a 1 right away. And in the next state, I'll go back to reset. That one's harder to conceptualize, I think. Yes?
On example, we have to know how to do both of these, or just more since you said we use it.
Question. I probably won't. I mean, technically, it's part of the material. I can't imagine why I would ask that. If I was, yeah, probably not. But I would. Yeah, it's not covered very intensely, but it's important that you know how to do the Moore state machine. Okay, so in fact, so actually this timing diagram is nice because it shows the Moore and the Mealy machine, so it shows them both. There's the input sequence, right? So there's 0, 0, 1. Sorry, it's my daughter. Okay, so there's the sequence. So we've got 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, and so the snail smiles after it receives a 0, 1, right? But notice that in the Moore machine, the difference is that notice that the Y, which is the smile signal, goes high in the cycle after 0, 1. You guys see that? Why? Because it's not going to smile until the cycle after it sees the 1 in the 0, 1 sequence, right? Because it's going to go through the 0, S0, S1, and then S2. In the Mealy machine, I mentioned earlier that the outputs in a Mealy machine are asynchronous because they're a function of the inputs and the state. So in the Mealy machine, there's a timing difference in that when you're in the S1 state and you get a 1 as the current input, that Y goes high right away. You guys see that? So you still get a smile after every 0, 1, But if you look at the difference, there's the output happens one cycle earlier than in the Moore machine. So the Mealy machine can respond right away to seeing a 1 because the output is a function of the state and the input. So the purpose of the state in the Mealy machine is only to keep track of whether I've seen a 0. It doesn't have to have all 3 states. Okay, so let's take a look at, how are we doing on time? 20. Okay, so how do you build state machines in Verilog? So far we've looked at how to do it in the 211 style, when you actually have to build them out of gates and primitives. In Verilog, you actually design the finite state machines in a way that matches up to the way you do it with logic gates. You have a next state logic section, which is its own always block. You have an output logic, which can be an assign or an always block. And then they have a state register section. So there's 3 parts. There's we used to call, in Verilog, we called this the clocked process. In this case, they call it the state register, meaning that you have one always block that has a clock. And then you have 2, the next state logic and the output logic, that are combinational logic, which in Verilog it would be always comb, or continuous assignment statement, assign statement. So the clocked part, the state register, takes care of reset, and it takes care of putting the next state into the current state whenever you have a clock edge and you're not resetting. And then the next state logic is what drives the next state, and the output logic takes whatever, in the case of a Moore machine, it sets the output as a function of whatever the current state is. Or if it was a Mealy machine, then we have to bring in the inputs into this output logic as well. Okay, now the other thing you'll notice is there's this syntax at the top where they declare an enumerated type for the state. This is one of the things they introduced in System Verilog that didn't exist in Verilog. In Verilog, as a Verilog programmer, when you design a state machine, you had to where's that example with the traffic light? So you had to come up with the encoding, the output encoding. Sorry, no, back up. You still have to come up with the output encoding. The current state encoding. So here, where we said that wrong slide again. Yeah, here we go. Where we established a mapping between the states S0 through S3 and the binary representation. You had to do this manually in Verilog. In System Verilog, they made it a little easier, where they allow you to create an enumerated type, in this case called state type, although you can call it whatever you want. And you could just list the states in there. You could actually name them in there. Now, to be honest, I always have to look this syntax up. I never remember the syntax for this. But they have type def, enum, logic, and then you still have to give it the number of bits. The number of bits is going to have to be, I don't know why it doesn't do that automatically, because the number of bits would have to be the log of the number of states. So there's 3 states, so the log base 2 of that rounded up would be 2 bits, right? So they have to declare it as 2 bits. Yes?
Maybe it's so that you could pre-allocate if you're prototyping and you don't have your full state space figured out yet. But you're going to need states later.
Yeah, that could be.
It's a lot easier to parse from a compiler standpoint.
Could be that, yeah, or it could be like, yeah, it gives you room for expanding the number of states. Yeah, I don't know. So you create this type called state type, and then you declare state and next state, and then you can use the states. The state type S0 is the reset, and then you've got S1 and S2 in there listed as well. So this is, you guys probably, Java has enumerated types, right? Enums?
Yeah, they're implemented as classes.
Oh, okay. Well, you learned it in C++ and 240, yeah. Yeah, so the compiler then would assign binary values to those, however it wants to do that. Okay, any questions? Okay, I'm not sure if I'll have time. Let's see, 20. We have till 30. We have 10 minutes. Actually, I might. Yeah, I don't. Okay, the next part is timing, and I'm going to hold off on this for next lecture because I'm not going to have time to get through all the material. I think this is a good time to stop.